Swayam Prabha. Digital India. Educated India.
LS. One is conducting. So I am going to show as though one is closed. This is closed. Right? Hopefully it has started conducting. So I am showing it as though it is closed. So this is inductance. Fine. Now this is conducting. I will have to have VCN. Please note I am writing VCN. This is LS. This is 5. This is 1. Both are conducting. Right? So A phase as well as C phase, both are active. And now this is connected together. And here is my RL load. Right? And the return is actually through 6. So there is only one device, which is 6. And then I am going to have LS. And I am going to have VBN. And then this is finished. Am I right? This is really the circuit during the overlap interval. Okay? So this is the circuit during overlap. Now if I try to look at it, this is point P. Let me call this as point Q. So between P and Q, whatever is the voltage, that is what is my output voltage. Right? The current that is flowing, I am assuming it to be a constant current, ID. We didn't want it to change. We said highly inductive load. So we said it is ID. We have neglected the ripple. If this is ID, right, I can say for sure that there is no variation in ID. So dID by dt equal to 0. If dID by dt is 0, there is no drop in this inductance. So inductance drop is 0. L di by dt in this particular case definitely will be 0 because the return current is a constant current, ID. Okay? So this does not have any drop. Right? Now I can say this is I1 and this is I5. So I can say clearly I1 plus I5 equal to ID. Right? Both of them make up for total ID. And both of them are returning ultimately through the device number 6. That's why we said device number 6 is carrying a constant current. Now, because I know dID by dt equal to 0, I can say dI1 by dt equal to minus dI5 by dt. This we already said. The rate of rise of current in 1 should be equal to the rate of fall in current in 5. That we already said, which we are writing again. That's it. Okay? Now, I have to say what is the voltage at this point and what is the voltage at this point. They are not going to be VA and VC respectively because the currents are increasing in one direction, the currents are falling in the other one. So L di by dt is definitely not equal to 0 in those cases. You get my point? I am going to have the voltage at this point as VAN minus L into dI1 by dt. And similarly here it is going to be VCN plus L into dI5 by dt. because di phi is anyway falling. So that is what I'm going to get as the voltages, right? So let me try to first of all see whether I can write the KVL equation for this and write the whole thing. That's simpler, right? So I can say KVL equation for this will be VAN minus VCN equal to LS into di1 by dt plus LS into di phi by dt, or minus LS into di phi by dt, because the current is in the opposite direction, right? I am assuming ideal devices. So if we include the device characteristics also, we are in for major trouble. That's why we are not doing that. We are only taking care of the transformer here. That's it. So I should be able to write this as VAC equal to 2LS into di1 by dt. Because di phi by dt and I1 by dt, they are of opposite. So have I written something wrong here? Is it plus or minus? Is it really minus? Look at that. I have written VAN minus LS into di1 by dt on this side. Agreed. This will be VCN plus I should have written LS into di phi by dt. So I am writing for some general current I. So I should write this as I and this also as I. So it should have been minus. This is general current I. Kirchhoff's laws, that I am talking about. So LS into di by dt, let that be I1, okay. And then the current is in the opposite direction. We are taking this current in this direction, which is opposite to that of I phi. So it is minus. So because of which it will become, this is minus, clearly. This has to be minus, because if we are taking this common current as I, it is in the opposite direction of I phi, which is okay, right? So I will get VAC equal to 2LS into di1 by dt. This is a very, very important result which we'll be using repeatedly, okay? So let me write first of all VAC equal to 2LS into di1 by dt, right? Now I can write this as VAC dt, instead of writing dt, let me write d of omega t by omega equal to 2LS into di1. I have not done anything else, just dt I have brought it on the other side. Instead of writing dt, I have written d omega t. So I have written a omega at the bottom. That's all. Nothing more than that. Okay. So let me just redraw again. This is omega t. I am going to have actually the current originally was like this, and then it is coming down as far as device number 5 is concerned. This is I5. As far as device number 1 is concerned, it is 0 and then it is rising slowly like this. So this is I1. That's all. And 1 was fired at alpha. I expected the current to abruptly rise to full value. It didn't happen. And there is an overlap. That overlap interval many of the books call as mu. So I am going to use the same notation, mu. So for a duration of mu, this rise in the current happens slowly. Right? And the rise in the current is happening slowly because of the source inductance. That is what is actually making it slower. So let me integrate this from alpha to alpha plus mu. And let me integrate this also from alpha to alpha plus mu, but my limit is I1. So I better say it is starting from 0 to ID. Am I right? So it will go from 0 to ID. Right? Is this clear so far? Now, let me take this omega there itself. So let me write this as 2 omega ls ID. That side is very simple. Not a problem. Now on this side, I have to write VAC d omega t. Alpha calculation is always done based on VAC. So we are very clear VAC can be written as Vm sin omega t. Straight. No problem. Right? So I can simply write this as Vm cos of alpha minus cos alpha plus mu. That's it. Right? This is what is my omega ls ID multiplied by 2. Right? So this is essentially VAC d omega t integrated from alpha to alpha plus mu. That's all. Right? Now, if I try to look at the voltage at this point, I told you already that it is either VAN minus Ls into dI1 by dt or VCN plus Ls into d phi by dt. So this point P is not anymore just VAN or VCN. It is not. So let us try to find out what is the voltage that will come up across the load actually during the overlap interval. It is not going to be just VAB or it is not going to be just VCB. It is going to be something else. So what is that something else? I have to check also because I don't know what is the voltage at point P. So I need to know the voltage at point P. So I should say voltage at point P, which is actually the top of the DC link. That has to be essentially VAN minus whatever is the voltage drop across LS. Right? You understand which is point P? I am talking about point P as the point here. This is what is point P. And this I am calling as point Q. So I am talking about voltage of point P, which is at the top of the DC link. Okay? So that is VAN minus whatever is the drop in this inductance. Right? So this is VAN minus Ls into dI1 by dt. Right? And we said that 2 Ls into dI1 by dt is VAC. So I should be able to write Ls into dI1 by dt as VAC by 2. So I can say this as VAN minus VAC by 2. Right? And what is VAC by 2? VA minus VC by 2. So I have VAN minus VAN by 2, which is first of all VAN by 2 itself, and there is minus VCN by 2. So minus of minus VCN by 2 is plus VCN by 2. So I can simply write this as VAN plus VCN by 2. Am I right? Okay? Just arithmetic manipulations, nothing more than that. Now voltage at point Q, not here. Voltage at point Q I know is VBN itself. There is no drop in the inductance and there is a current flowing. So this device is a short circuit. So VBN is the voltage at this point, at VQ. So I can say VPQ is equal to VP minus VQ, VQ being VBN. I can write this as, this is the VDC link voltage. So this is equal to VAN plus VCN divided by 2 minus VBN. This VBN, let me just divide it into VBN by 2, VBN by 2. So I will have VAN minus VBN by 2 plus VCN minus VBN by 2. So it will be VAB by 2 plus VCB by 2. If 5 had been conducting, I would have gotten VCB by 2. Only 1 had been conducting, I would have gotten VAB. So it is the average of the two. That's what it means. So I am going to have this to be VAB plus VCB by 2, which is the average of either 5 conducting alone or 1 conducting alone. So now I have to compare the voltage without overlap with overlap. Without overlap, I would have gotten VAB. With overlap, I am getting VAB plus VCB divided by 2. So VAB minus VAB plus VCB divided by 2. This is the difference in DC voltage because of overlap. Right? So this is going to be VAB by 2, VAB minus VAB by 2, so VAB by 2 minus VCB by 2. Right? And VA minus VB, and this is VC minus VB, so VB will get cancelled. It will be simply VAC by 2. Everywhere this VAC fellow is coming. Wherever we look at any increase in the current, any detriment to the increase in the current, any drop in the voltage, everywhere this VAC is the fellow who is influencing, because we are transferring from 5 to 1. 5 is C, 1 is A, so we are getting VAC repeatedly coming up, right? And this VAC by 2 we already said, we had integrated this, if you may recall, we said integral VAC d omega t from alpha to alpha plus mu was 2 omega ls id. So if I integrate VAC by 2 from alpha to alpha plus mu, where I am having this as the voltage drop or reduction in the voltage in the DC link, that will correspond to omega ls id, not 2 omega ls id. Instead I will have omega ls id. I am trying to recall this. Basically I am saying that if I do the integration for the duration from alpha to alpha plus mu, at what point overlap is happening, that is where there will be a drop in the DC link voltage. And the DC link voltage is dropped by a factor of VAC by 2. That's what we decided just now. And VAC by 2 is the drop which has to be integrated from alpha to alpha plus mu. So let me draw the waveform here. If I had drawn the waveform corresponding to the actual value of voltage, I should have drawn the voltage, alpha had been 60 degrees for example, I should have had the voltage like this. This should have been the voltage VAB without commutation overlap. If I had drawn the VCB, VCB should have been like this previously. Are you getting my point? Without commutation overlap, this should have been VCB, this should have been VAB, and so on for alpha equal to 0 degree. For example, now, alpha equal to 60, sorry. If I am talking about overlap, at this point, I am not going to have the overtaking of, so I am going to have VCB coming up as the average between VCB and VAB as the DC link voltage. So, VCB is coming down further like this. VAB is like this. I should take the average between the two. The average between the two will be somewhere here. You get my point? Because this is VCB. VCB is definitely going below 0. So, I am going to have during the overlap, this is going to be the output, and then it is going to jump up to VAB again. So, this is VAB. This is VCB plus VAB by 2. So, for some time it is going to dwell on the average between VCB and VAB by 2, and then it is going to jump up to VAB. So, this is the portion which is lost because of the commutation overlap. So, the DC link voltage is going to come down because some amount of voltage is dropped in the inductance. Just can't help it because the inductance will not allow abrupt changeover of current from 0 to maximum value or maximum value to 0 value right away. So it happens slowly. In the process, there is an inductance drop. That drop is manifested in the form of a DC link voltage drop. Right? So I have two simultaneous happenings because of the source inductance effect. One is I am going to have reduction in the DC voltage, and the second one is there is going to be definitely a delay in the current taking over from one device to another. What are the further repercussions of commutation overlap? We look at it in the next class and wrap it up.